periodic classification of elements. Let us study the early methods of classification. To study the need for classification of elements. Michelle has a free period and wants to go through a comic book. Well, Michelle is having a hard time to find a favorite book. And now, Michelle has to leave frustrated. The reason being, misuse of her precious time by having to group through the pile of books. Let us try a different situation. What if the books were arranged systematically? That's so convenient for Michelle as she knows exactly where to look for the book she intends to read. Similarly, there are about 114 elements known to man. How about studying their individual properties? Oh, that would have taken ages, as these elements combine among themselves to form millions of compounds. Now, scientists needed a convenient approach to study the properties of each of these elements. That is the very reason that these elements have been grouped together. To begin with, Daubonier's triads. Triad means group of three. In 1803, Dalton published a table of relative
atomic weights.
This was an important base towards the classification of elements. However, later in 1829, Daubonier reported that there are few triads of chemically similar elements. When these elements were arranged in group of three, in order of the increasing atomic masses, then the middle element has the atomic mass and properties roughly the average of the other two. Let us take a look at the first group of triads. Here, the atomic mass of lithium is 7. Atomic mass of sodium is 23. Atomic mass of potassium is 39. Now, let us derive the average of atomic masses of lithium and potassium. This shows that the middle element has the atomic mass and properties roughly the average of the other two elements. Now, what is the significance of Daubonier's triads? The atomic mass and the properties of the middle element could be predicted. Is there any drawback of this method of classification? Since there are very few elements that could be arranged in triads, the prediction of atomic masses and the properties of other elements were not possible. Newland's octaves. In 1864, Newland arranged the elements in the increasing order of their atomic masses. He observed that the properties of the eighth element is the repetition of the first element. This is just like the notes of the music. This was called as the law of octaves. The elements were arranged in the group of 8, hence it's called as octaves. From the table it was observed that the properties of sodium and lithium, which is the eighth element, were similar. Hence, the need for arranging the elements into vertical columns called the groups and the horizontal rows called the periods became evident. It was easy to observe the periodicity in the properties of the elements. Mendeleev's periodic table. Dmitry Mendeleev presented a more scientifically useful table of elements. Mendeleev saw that there is a periodicity occurring in the physical and chemical properties if the elements were arranged in the order of their atomic weights. In Mendeleev's time, there were about 60 to 70 known elements. In the periodic table, the elements were grouped in such a manner that elements showing similar properties occur in the same vertical group. For example, he placed
titanium
under silicon as he saw that titanium and silicon had similar properties. Tellurium was placed before iodine, though it had higher atomic mass. This was done because iodine had properties similar to that of bromine and not selenium. Mendeleev's periodic law states that the properties of elements are a periodic function of their atomic masses. The elements are arranged in such a manner that the vertical columns are called groups and the horizontal columns are called periods. Elements in each group have similar physical and chemical properties like valency, melting point. The periods are made with elements written in rows of increasing atomic masses. As one goes vertically downwards in a group, the elements show increase in atomic volume. The first two periods are similar to Newland's law of octaves. Apart from this, there is something ingenious about this table. What is it? Well, Mendeleev placed elements that have similar properties under vertical columns, even if other elements were not found. Thus, there was a gap below
aluminium
in the group and after calcium in the horizontal period. As if this were not enough, he also found it necessary to leave gaps altogether in his table. Rather than considering these gaps as imperfections in the table, Mendeleev said that they represented elements as yet undiscovered. He named the unknown elements as
Eka aluminium,
Eka silicon. Eka is the Sanskrit word for one. Drawbacks of Mendeleev's periodic table. The position of isotopes could not be accommodated within the table. In order to make the elements fit the requirements that those in a particular column all have the same valency, Mendeleev was forced in one or two cases to put an element of slightly higher atomic weight ahead of one that is slightly lower in atomic weight. Thus, tellurium, that has an atomic weight 127.6, had to be put ahead of iodine, whose atomic weight is 126.9, in order to keep tellurium in the valency 2 column and iodine in the valency 1 column. Let us see the success of Mendeleev's periodic table. When Mendeleev presented his periodic table, inert gas elements like helium, neon, and argon were not discovered. When they were discovered, they could be neatly put in as the last group of elements without disturbing the rest of the table. His predictions about unknown elements from gaps in his table were a great success. Scientists who repeatedly discover newer and newer elements follow this feature.